takes that proportional symbol and he makes it into an equal symbol. And this is how he does it. He says, he comes up with the equation that the force that a planet would experience is going to be equal to this constant, capital G. I'll get to what that is in a second. The mass of the planet, the mass of the other thing that it's pulling against, so in this case might be the sun, divided by the distance squared between them. So he took this and he really specified it into this. This is the one that you're going to find on your physics reference tables that you have to be able to use. So let's make sure we can define some of these. This is the force between the objects. And that's in newtons. Now, I wrote objects. I've been saying up until this point, it's the force between the sun and the planet, or two planets. I've been using those terminologies. But what I want you to know is that Newton realized that this equation doesn't just apply to planets. It applies to everything. So this equation, which says you have two objects with mass and a distance between them, and that'll make a force, any two objects can apply to this equation. This is where it gets amazing. We can say student A is sitting next to student B. They both have mass. Student A's mass, student B's mass. There are a certain distance between each of them. And we can plug those numbers in and it will tell us the force of attraction or the full force of repulsion between those two students. Truly, this equation works. Now it's much more pronounced or much more obvious when you're talking about planets because the masses are so huge that makes the force huge. If you're talking about little things like a nucleus and an electron, two small things, well, the force is going to be really small too. Okay? But as things get bigger and bigger and bigger, this force becomes more obvious. So anyway, continuing on. This big G is called the universal gravitational constant. It's a big verbose name, universal gravitational constant. But what I want to point out, you can't get it confused with gravity. It's not gravity. Gravity was that thing, the acceleration of gravity, lowercase g, not the same. Don't confuse them. This is the universal gravitational constant. It only applies to this equation because Newton just had to figure out how to make it from proportional to equals, and this is the number he came up with. It's a 6.67 e negative 11. 6.67 e negative 11 is newtons times meters squared over kilograms squared. So it's an awkward, difficult number, but your calculator can handle it just fine. Each of these things are masses. They're in kilograms. And this is the distance between the masses. And that'll be in meters. So when all is said and done, we can do an example, which we will right now. Make sure we know how to use this thing. So again, as I go to my book here, I can find an example, like example 37 here. 37 says, assume you have a mass of 50 kilograms. So we got a mass, we'll call it number 1, 50 kilograms. Problem 37. Mass 1 is 50 kgs. And the Earth has a mass of 5.97 E24 kilograms. Did you know the mass of the Earth before this point? Well, there it is. There's the mass of the Earth. And the radius of the Earth is 6.38 E6 meters. Pretty big. Well, if you're standing on the surface of the Earth and you weigh 50 kilograms, how much gravitational force are you experiencing? In other words, because of your mass and the Earth's mass and the radius of the Earth, because here, let's draw the picture. Here you are. There you are, standing right there. Because of the radius, from there to there, you're experiencing this force. How much is it? So, let's figure that out real quick. We start with our equation. F equals big G m1 m2 over r squared. We're going to plug in the big G, which is 6.67 e negative 11 newtons meters squared over kilograms squared. Yes, awkward, but throw it right in there, don't worry about it. The mass of you, 50 kilograms. The mass of the Earth, 5.97 e24 kilograms. All over 6.38 e6 meters. Now here's where a lot of physics students stumble, trip, and make a mistake. This number on the bottom, you gotta square it. You gotta square it. If you forget to square it, you're gonna be way off on your answer. What I usually tell people to do is square this first, write that down, and then multiply these and divide by that number you got when you squared. I'm not going to take up any more time on the video, but basically if you plug in your calculator and you do all this work correctly in the correct order of operations, you're going to come out with a fairly simple number, which is 498 newtons. No, 489. 489 newtons. So, how is this different than what we did before? Like what we did before when we wanted to know someone's weight, how did we come up with someone's weight in the olden days? Joe?
Multiplied their mass by the force of gravity.
So you took the mass of this person, 50 kgs, and you would multiply by 9.81 meters per second squared, which is going to give you about what? What you got, Kyle? Joe? 490.5. See these two numbers? Very close. This big equation, which is big and cumbersome and kind of nasty to use sometimes because of the numbers, works all the time. This equation right here, the FG equation, this only works when you're close to the surface of the Earth. This is like the figure out the weight when you're standing on Earth equation. This is the equation, you can figure out the force between any two things anywhere, in space, anywhere. It always is going to work, but I wanted to point out the fact that those two are really similar, but one has a more specific application. And one, the new one, is much more universal. So for today, physics.